Okay, everybody, welcome to our this week's physics colloquium. It's our great pleasure to welcome Professor Nick Rod from Lawrence Berkeley National Laboratory to give this week's colloquium. Nick is a compatriot of mine. He started in Melbourne and then went to MIT for his PhD and Berkeley and CERN for postdocs before landing at LBNL just a few months ago. And Nick is a particle phenomenologist working very widely, especially in dark matter theory. And he's done a bunch of very important things, but the thing that he'll talk about today, and perhaps one of his major areas, is the theory of sort of light hidden sectors and light dark matter candidates, especially the various non-trivial ways in which we could possibly...
Doesn't look too silly. Okay, very good. So what I would take from these observations is that we actually know a lot about dark matter. Of course, I'm going to tell you today that there's not everything we know. I'm still very much employed, but actually there are some definitive things that we don't, there are some definitive things we do understand. And in particular, I can tell you very quantitative statements like that of the matter budget in the present universe, 84% of it is made of dark matter. So that's a very precise statement that I can make. And furthermore, coming from a particle physics background, what I can tell you is that whatever this dark matter is, it just has to be some new particle that we haven't yet discovered. Of course, maybe at first blush, you'd think this is ridiculous. I'm telling you about a deviation in our observations at the smaller scales of the sizes of galaxies. And I'm telling you that the resolution to that problem lies at the subatomic level. However, of course, if you think about it for a moment, it's maybe not as preposterous as it first sounds, because everything we can see in these images, we know to ultimately be made of particles. And really the great miracle of particle dark matter is that I can add an individual particle to the standard model and make all of these observations consistent with our theory. So that's the great success of particle dark matter. Where this idea runs into challenges is if you start asking me specific questions about what exactly this particle is. So of course, particles have many defining properties, and probably the first one you think about is what is the mass of that particle? So let's ask a simple question: what is the mass of particle dark matter? And here is where I have to be honest that at the moment we are hideously ignorant of the answer to that question. So to give you some context, I'm showing you one way of measuring dark matter here on this ruler. And on the top, I'm showing you the range of masses of particles we have in the standard model, and even extended to include the neutrinos. Now, as I'm sure many of you will be aware, there are enormous questions we have in the standard model about why are these particles distributed over such a vast range of masses. However, you can see from this that compared to that, where dark matter could live is enormously broader. In fact, I'm actually lying to you here. I'm only showing you from 10 to the minus 10 eV up to the Planck scale of about 10 to the 28 eV. But in fact, in truth, dark matter could have a mass all the way up to a solar mass, which is about 10 to the 57 GeV, or it could have a mass all the way down to maybe 10 to the minus 20 eV. So it'd be a much larger scale if I showed you the full range of it. So of course, this represents a challenge, but also it represents an opportunity. And the reason for this is that as we look at the different mass scales, the dark matter could behave very, very differently, and it opens up new opportunities for how we could search for it and how we may have not discovered it so far. In particular, for good reasons, much of our thinking for decades now has focused on this, what I would call this sort of classic window. This is where the dark matter has a mass that is not that different to the particles we've discovered in the standard model. And there are many reasons to think this is where the dark matter mass should be. We have many questions open in the standard model, and maybe dark matter could play some fundamental role in resolving them. And in many of those scenarios, you end up with a particle mass that's not too different from the ones we've discovered so far. So that's a very important window and one which we continue to search in. But of course, we haven't seen anything there so far. So as a field recently, we've been thinking more broadly, maybe the dark matter mass just isn't in this classic window, maybe it's in a broader window. And indeed, I want to tell you about one of the new windows that has really emerged in the last decade in the talk today. In particular, what I want to focus on is the possibility that dark matter could be very light. And if it has a mass below 10 electron volts, what we know for certain is that locally, given the energy density we observe, is that the states must start to be overlapping. You can compute what their associated de Broglie wavelengths would have to be, and you'd have to have these states individually overlapping. Firstly, that tells you they must be a boson. But additionally, what you learn from this is that you'll get a qualitative change in the behavior of dark matter. You should no longer think about this as particles flying around in space. Instead, what you should think about is it behaving like a coherent wave that we could try and detect in one of our instruments. So if it's behaving like a wave, it's no shock that we haven't detected it so far. We'll need a completely new type of detector to look for it. So just as the WIMP is sort of the poster child of the classic window, I would say what has become the primary candidate people focus on when they're searching for wave dark matter is something called the axion. So if you haven't heard about the axion before, I'll give you an introduction to what we think about it and what's where we are and where we hope to be. In particular, the main way that we search for axions, independent of how well they're motivated, is that we think that they should couple to electromagnetism through the following Lagrangian interaction I'm showing you here. So here, A is this axion particle. It's some pseudo-scalar boson. And we expect that it couples to the electromagnetic field strength and its Hodge dual. So technically, this is a dimension 5 operator, which means that this unknown coupling constant between the axion and electromagnetism has to have inverse mass dimension, and that will be relevant at 1 or 2 times in the talk, so I just mentioned it here. But practically, what this means is we've got some new term in the fundamental interactions of nature. What we want to do is then crank the handle and see how would that change the various laws that we have of describing the world around us. And one thing we can see is because this couples to electromagnetism, we might expect it modifies the laws that we have of describing electromagnetic interactions. And indeed, you find that this modifies the inhomogeneous Maxwell's equations in several ways, but the one that is most important is that in the presence of a magnetic field, an axion will induce an effect that looks like a current. So we can look for electromagnetic effects. We're very good at that. We can build very sensitive devices. And the idea is that if axions are dark matter, maybe we could look for a current that it induces and actually see some signal of this. So I'll come back to say some more words about how this actually operates later on. But what I want to do now is just tell you, given that vague idea, where are we in the search for axions and where do we hope to be in the next few decades? So in order to map out the parameter space, what I'm doing is I'm showing you the unknown mass of the axion here on the x-axis. You can see I'm covering quite a few orders of magnitude. I've got 20 there. This is, of course, just a subset of the broader problem that we don't know what the mass of dark matter is. And what I'm showing you on the y-axis is its unknown coupling to electromagnetism, which technically has inverse mass dimension. So I've just given it dimensions of inverse GeV, as is customary in the literature. So looking for axions is very challenging, but it's not as challenging as I'm representing on this slide. We actually know a lot. I'm just going to build it up step by step. So to begin with, if I don't even assume the axion is dark matter, the axion could just be some state that exists in the spectrum of nature. I actually can exclude the possibility that it is very strongly coupled to electromagnetism. Broadly, the intuition of these bounds that I'm showing you in light gray here is that if this state exists, then potentially if you have areas where you have very hot and very high energy photons, they could emit axions. One example of this would be stars like the sun. They could be emitting axions, and then either you can set constraints from these stars cooling too quickly, or alternatively, you could even point an LHC dipole magnet at the sun. This is what the CERN CAST experiment did. Look for the axions coming in, converting into X-ray photons, and when you sadly don't see anything, you can set very strong constraints. That's what CAST did. This is an idea that people have been thinking about for a long time. There's still a lot of active physics in this. I've been thinking about this. I gave rise to these very funny looking contours up here in the search for these types of particles. But broadly, we haven't seen anything so far, which just tells us that if an axion exists in nature, it can't be too strongly coupled to E and M, or we would have already seen it, which is maybe not too shocking. So these do not require the axion to be dark matter. But if I now make the very strong assumption that axions are also dark matter, I can get another a set of constraints which come from the fact that this interaction here would actually destabilize the dark matter. If the axion couples to 2 photons, well, then it should be able to decay to 2 photons. And in fact, if I sit down and compute what the decay rate of that is, I'll find because this is a dimension 5 operator, the decay rate will have to scale as the mass cubed just to make up the dimensions. And so that means as I go to higher masses, this decay rate will become more and more relevant very rapidly. And in fact, where these constraints are coming from that I'm showing you in dark gray here, I should go and look for photons coming, a line of photons coming from regions of dark matter, because this would be how the axion would decay in these cases. Again, we haven't seen them. And so we set broadly these set of constraints that get stronger and stronger as we go up, because again, the decay rate is growing very rapidly. It goes as the mass cubed. So that tells us that we cannot live up the top or to the right, but then there's many, many orders of parameter space where the axion could live in the lower left and be dark matter. Of course, we can go to our experimental colleagues and say, please cover as much of this parameter space as you can, but I know that that is challenging and time consuming, so probably more useful is for theorists to sit down for a moment and think, well, where do we really believe the axion lives in this parameter space? And one of the reasons the axion is such an exciting dark matter candidate is that we do have a prediction for where it should live here. In particular, in addition to being a very well-motivated dark matter candidate, the axion could also resolve one of the long-standing problems we have in particle physics, which is the so-called strong CP problem. However, I mean, just from the name, you can understand that the strong CP problem has something to do with the QCD interaction. And so in order to resolve this, the axion would have to couple to the QCD field strength. And in fact, the stronger it couples to the QCD field strength, what will turn out is it will gain a larger mass. These QCD interactions will actually give a mass to the axion in such a way that the stronger the interaction, the larger the mass it generates. And so we end up having a prediction that the stronger the coupling, the larger the mass for the axion that it should be. Now you can see I'm not showing you a line here, I'm showing you a band. And the reason for this is because what I have a strong prediction for is what would the mass be for a given coupling to QCD, but I'm not looking at the coupling to QCD here. That's generally very hard to look for, although not impossible. I'm showing you the coupling to photons, and then depending on your specific model, I can wiggle those around a little bit, and so that's why a line ends up turning into a band. But broadly, if an axion that resolves the strong CP problem is the dark matter of our universe, we expect it to live somewhere along here. So that's really the target where these instruments are going after. So with that in mind, how are they doing at the moment? So let me show you what is the current reach of these Axion Haloscopes, which was again in the title of my talk today. And just to tell you where this name comes from, these are instruments that are looking for axions that make up the dark matter halo of our universe. That's why, or the dark matter halo of our Milky Way. That's where this name comes from. And you can see if the axion mass is in the sort of micro EV range, it is an incredibly exciting time because instruments like ADMX are already cutting into the most well-motivated parameter space, and other instruments like Haystack will cut into this very soon. I think it's no exaggeration to say that any day now on HEPX, we could just have the paper posted saying that ADMX has just detected the dark matter of our universe. So it's an incredibly exciting possibility, but is very plausible given the parameter space that they're cutting into. However, if you step back for a moment, you'll realize that that's not the only part of the parameter space where axion dark matter could live. In principle, it could be much heavier, or it could be much lighter. And then if you stare at this for a bit longer, you might become very pessimistic. Because while at micro EV mass ranges, you can see we're doing very well. If we go down to these lower mass ranges, you can see that these instruments aren't even yet getting below the star emission bounds, and yet they've made the extremely non-trivial assumption that they're also looking for the dark matter of our universe. So that's a pretty non-trivial assumption. So why would anyone show these to you other than the fact that they were personally involved in one of these instruments? Well, the reason for this is that the scientific reason is that these were proof of principle devices. For example, Abra 10 centimeter was only about the size of a grapefruit. It was just meant to be a prototype. And over a wide range of the frequencies it searched in, it actually hit its theoretically predicted noise floor. Now, of course, there'll be many challenges, but what that gives us confidence is that as we build bigger versions of these instruments, we should be able to drive them down. And what's been shown is that actually these devices have a very good volume scaling, even better than these cavity instruments here. And the hope is that combining larger versions of these instruments with new search techniques like moving from broadband to resonant readout, we could significantly improve the reach of these instruments in the coming years. In particular, the ambitious but I think achievable goal of the dark matter radio program, which is the extension of these ideas like abracadabra that I mentioned here, is to cover the entire parameter space I'm showing you in blue here, which will cover several orders of magnitude of the QCD axion parameter space and also broadly move through many orders of magnitude of unexplored space. And this is just one of many ideas that are being put forward in the literature. I don't have time to go through them all, just to flash a few more, but there are more than dozens that have been proposed. We have many ideas that we could live. And a question that has kept me quite interested over the last few years is to think, as we drive towards this, is there anything else we might be able to run into with these instruments? So in particular, as I said at the outset, I want to tell you about two specific possibilities, although I think there could be many answers to the question that I have on the slide here. And in particular, I'll tell you about the possibility that we could have an axion analog of the cosmic microwave background that could show up at these instruments. And secondly, I'll explain to you how even a different type of wave passing through them could be detected. In particular, if you had gravitational waves at high frequencies, you would also induce a response in these devices. So I've already had a lot of preliminary material, but just please allow me one more minute, because other than some vague words about modifying Maxwell's equations, I haven't told you about how any of these detectors actually work. So let me just describe to you how they operate at a very cartoon level and how the discovery of dark matter could work at these instruments. And I'll use that to then give you some ideas for how you could look for these other signals. So again, as I told you earlier on, although there's several modifications, the dominant modification we care about is the one to the Ampere-Maxwell law, where we find that in addition to the normal predictions you study in electromagnetism, we find that in the presence of a magnetic field, an axion will induce what by analogy looks like a current. So that tells me that if I want to detect this, the first thing I need to do as an experimentalist is build a very powerful magnet. Of course, there's various magnet geometries one could pursue. All of them are possible. The one I'm showing you here is just the one that's closest to my heart because this is what we used in the original abracadabra prototype. But I'm just taking here a toroidal magnetic field. So that's the first ingredient. Unfortunately, that's not enough to make a detection. You need a second key ingredient, and that is that you actually need the axion to be dark matter. Otherwise, nothing's going to happen here. So if the axion is dark matter, it would be some oscillating wave passing through this experiment. And what we saw from the modification to Maxwell's equations is that the interaction of the two of these will give rise to some current that is proportional to the magnetic field. However, the sign of the current will oscillate backwards and forwards in time because it's linearly proportional to this oscillating wave. Okay, so we've got this current where we had magnetic field lines. How are we going to go detect it? Well, this is something you can understand just by remembering your elementary electromagnetism. In particular, what you need to remember is the right-hand rule. And what you can see is that what this current will do is it will generate a magnetic field in the center of the torus, or at least ideally, there should have been no experimentally generated magnetic field. So you can see this magnetic field is going to be induced here. It will also be oscillating in time. And so if I put a pickup loop here, I should get some oscillating flux coming from this magnetic field at a frequency associated with the axion. So if I take very accurate time series data of this and take a Fourier transform of it, eventually I'll see a spike at the unknown axion mass, and that excess power I see at that mass would essentially be what the discovery of dark matter looks like in this picture. Of course, in practice, there are many backgrounds one needs to contend with, and it's much more complicated than I just described, but at least in principle, that is how it would operate. Now, as I turn to the first alternative signal that we can look for at these detectors, just to say, notice that at no point in the discussion I just went through did I require this wave to be non-relativistic, which is the hallmark of dark matter. So if I had relativistic axions passing through these instruments, there will be differences that I'll discuss, but in principle, the same thing would occur, and I would also get a signal in here that I could then go and look for. And with that in mind, this has encouraged some thinking that I've had in recent years about looking for these additional signals, in particular this idea that we dub the cosmic axion background. Primarily, the work that I'll be telling you about today was motivated by something that I did with my collaborators, Jeff Draw and Hitoshi Murayama, a couple of years ago now, but it's really also impacted some of my more recent thinking I did with the ADMX collaboration, and also with my other collaborators, Stefania Gori and Jacob Leadham. So I'll get into the specifics of what's happening here, but if you just take the answer to one question away from this part of the talk, all I want to impress upon you is that it is possible to detect these types of early universe axions using these Axion Haloscopes that were designed to look for something else. They're designed to look for axion dark matter. So in order to go through this, I need to tell you about how these signals will look different because they're going to be quite different to dark matter. So I'll run through this picture of the landscape. Previously, remember, we had the axion mass on the x-axis, and we had the coupling to photons on the y-axis. I'm going to do something different here. What I'm showing you in this case is I'm showing you the frequency or the energy of these states on the x-axis. And the reason I'm showing you for this is that, recall, these instruments are looking for some signal at a given frequency. And the frequency that a particle oscillates at is set by its energy. So for a non-relativistic particle, its energy is its mass. So I can match the frequency to the mass range I'm looking at. For a relativistic state, its energy is its energy. Its mass is effectively irrelevant, and that's what I'm going to be treating for the talk today. And so I can match the frequency or energy ranges I'm looking at to the same frequency ranges that were looked at various instruments like dark matter radio or others that are covering this parts of the parameter space. So that's what's on the x-axis. What I'm putting on the y-axis for you is how much energy density is there in these relativistic waves at a given frequency. So technically, for those of you who follow this literature, I'm defining it in the same way that people talk about the energy density in stochastic gravitational waves. But just to say, the reason I need to specify this is that for dark matter, this wasn't a free parameter. I know from observation of the motion of stars around us in the Milky Way that there has to locally be some dark matter at an amount of about 1 proton mass worth of dark matter per cubic centimeter. For this cosmic axion background, it need not be there at all. So I have to specify how much energy density is there if I want to think about its detectability. Of course, the coupling to photons still matters, and I'm hiding it at the moment, but I'll come back to that in a couple of slides. So just to give you some intuition for where you are in this parameter space, if your integrated energy density is around this dashed line here, you have an energy density in the cosmic axions that equals the energy density in the photon background or the cosmic microwave background, and you would also be living in a universe that's not our own. The reason for this is that we know from our measurements of the expansion history of the universe taken from the CMB and Big Bang nucleosynthesis that there cannot be too much additional radiation or it would observably modify the expansion history of the universe. This is codified in this famous delta N effective. And so we know by delta N effective, you need to live, at least in integrated sense, below this line here. However, that would also be the most exciting part of the parameter space, to live a little bit below this dashed line here, because not only might you be able to detect it in the ways I'm going to tell you about today, eventually you would also expect to see some modification in future cosmological observables, potentially CMB stage 4, for example. So having laid out the axes, let me put some candidates onto this plot, like what could the cosmic axion background actually do to populate this space? And the idea that comes first to my mind, and maybe to some of yours as well, is that maybe the axion could exist in direct analogy to sort of how we have the cosmic microwave background. The picture here would be it couples somehow to the standard model. So at high temperatures, the axion was in thermal equilibrium with all the other states. It was there in the primordial plasma. But we know it doesn't couple too strongly. We have quite strong bounds on this. So eventually it decouples. And then that essentially black body spectrum just redshifts until today. You can actually make, it's a very robust prediction that if that occurred, you should have some distribution that is also peaked at around a microwave for the same reason that the CMB is peaked there. And you also roughly know what its energy density would be. So for me, this is the most attractive target. But to be upfront, the ideas I'm about to tell you won't get close to this. We're going to have to come up with some other idea, and I'll hopefully give you some physics intuition for why that's the case. But that's all right, because this is just one of many ways we could imagine producing axions in the early universe. Many have been discussed in the literature. Just to give you a couple of my own favorites, cosmic strings are generically associated with axions, and they could copiously radiate them over a largely scale-invariant spectrum. Parametric resonance is a phenomenon we think for various reasons could have occurred in the early universe, and that could also produce axions. And even axions could be produced in the late universe. Earlier on, I told you about one way of searching for dark matter was looking for its decays to photons. Maybe dark matter decays to axions. And if that's the case, you could actually get a very large energy density coming from the fact that there's a huge energy density in dark matter. And these are just a few examples. Many have been discussed in the literature. This is just to say is that this parameter space could be populated. And then the question is, could you detect it? So as we move towards this, the question that I first asked about this, and I think is usually a useful question in these types of searches, is the energy density we're considering in the wave-like or the particle-like regime? Remember at the outset, I said that our search for dark matter is hugely influenced about what part of that parameter space we're living in. Well, this is true for any bosonic energy density. And so for these cosmic axions, I have to re-ask the question, for a given energy density and frequency, are the states overlapping or not? And when you run through the calculation, you find that the dividing line is the dotted one I'm showing you here. And if you're well to the left of it, you really can think about what you're doing as being described as a wave. So of course, again, this whole picture of this wave-particle divide is somewhat hand-waving, and it's a question that's bothered me for a long time and I've been thinking about. But for today, you can really think that if we're looking at these lower frequency candidates, the description at the location of the detector is just a classical wave, which is great because these instruments were built to look for these classical waves, so we will be able to port over a direct analogy. So let me try and make this picture of the wave somewhat more precise to at least tell you how there's some difference between these relativistic axions and the dark matter ones. And as I do this, I can tell you that a pretty good picture for waves, in fact, a reasonable description of the wave that's coming out of the light bulbs above us, is that you can think about it as just some wave as a collection of different frequencies drawn from some distribution of the frequencies, which could be, say, that thermal distribution I showed you previously. But other than that, there's no generic reason to expect the frequencies to be phase coherent. So I just add some random phase associated with them. So what does that actually look like? I mean, and just to say, I put tilde here, but I can make this all equality by putting in, say, the energy density, for example. I'll distill the essential physics of the difference here. So if I draw up what dark matter would look like, I'd get the plots that I'm showing you here. So the three different colors are three different statistical realizations of what the dark matter field could look like, which vary because of the stochasticity in this random phase I'm showing you here. So you can see that the exact amplitude will fluctuate around a bit, but what does not change is that the oscillations are extremely regular in the dark matter case between all of the realizations here. If I move to this case where I draw these relativistic axions from a broad frequency distribution, instead I'll find that the oscillations are, even though there's this fluctuation in the amplitude, as a function of time, they move around enormously. They're not at all regular in the way that the dark matter wave is. So of course you can describe this in the time domain. It's a slightly harder analysis, but one can do. But a lot of the physics here becomes elucidated when you take a Fourier transform of this and look at what's happening in the frequency domain. In particular, what I would find if I tried to compare these signals, dark matter would look like essentially a delta function at its mass, whereas this cosmic axion background generically will just be some broad distribution of frequencies that I'm searching at. Now, dark matter isn't literally a delta function, because recall that the frequencies are controlled by the energy, and not every dark matter particle has an energy set by its mass. They do actually have some velocity dispersion, but we know that locally, the velocity dispersion of dark matter should be about 10 to the minus 3 in natural units. So that means the corrections to the energy, which are famously encapsulated in a half mv squared, will be about the size of 10 to the minus 6. So I have to zoom in by a factor of 1,000,000 to see there is a distribution of dark matter here. It's just much, much narrower than I would get from some generic relativistic distribution. So this is in some sense one of the key differences between these two signals. And for example, it tells you that if you went to go and search for this, for dark matter, you're looking for some narrow spike that shows up in your distribution. You don't know where it is, but that's what you're looking for. Whereas for these relativistic axions, you're looking for them to deposit power over a broad range of frequencies. And it turns out from an analysis perspective, this very much changes how you want to search for it. In fact, it's such an important parameter, I just want to quickly define a quantity that I'll carry forward in my estimates for it. I'll define this quantity that I call a Q factor, which is a dimensionless measure of the inverse width, which in practice means that if I make the distribution narrower and narrower, I make this Q factor larger and larger. It's defined in the same way as you have Q factors for simple harmonic oscillators, if people are familiar with that. So for dark matter, it has a very large Q factor. For the CAB, it'll be generically order 1. And so if you want to go and look for this broad energy distribution in these instruments, I can tell you actually the way ADMX, one of the leading instruments, searches for this at the moment, is they just subtract this, they smooth their data set off, subtract the smooth component, and don't even save it to disk. They throw it out because they're looking for a spike. So if they even had a CAB signal on their data set, they never stored it. So actually, one of the things that I did with the ADMX collaboration was come up with a new analysis strategy in order to get beyond this. It involved a number of details that unfortunately I won't have time to get into today, but I'd be very happy to talk about afterwards or offline. So that is if this signal is even detectable that I haven't told you about yet. And there are various ways of estimating this, but just to give you a quick hand-waving derivation, it's a useful quantity to compute is how much power is there accessible in this axion wave. I can compute the power in the axion wave, but that's just very much an academic exercise because I can't directly see that. The only way I can measure power from axions is through this very small coupling that they have with the standard model. And technically, there has to be a derivative because they're pseudo-Goldstone bosons. So if I can compute the power that I could actually hope to access in the axion, I find it has this form here. Coupling squared depends on the energy density and also depends on where that power is distributed in frequency. The other factors come out of the detailed calculation, but they don't change what's going on significantly. Now, of course, I could study this for different versions of this probability distribution, but here is where this Q factor I introduced is very useful. And the reason for this is that I can roughly parameterize the probability distribution as having the form of the Q factor divided by the mean frequency to make up the dimensions. The reason for this is that something that all probability distributions obey is that they integrate to 1. But if I have this power distributor of a very narrow frequency range, if it wants to integrate to 1, it better have a very large value. And so you can confirm that for a large Q, it has a very narrow range, therefore it has to have a very large value of the PDF. And so it actually ends up being that you get the enhancement in the power at the given frequency you're looking at. So this is now just a qualitative form for the power at this central frequency I'm considering. And I could apply this estimate to any form of axion wave. I never told you I was looking for dark matter or for the CAB. I can use this estimate for both. And now I can get a rough estimate for how sensitive I should be to the CAB by saying, well, I know what dark matter powers I'm sensitive to in existing or forecast instruments. I'll just say the CAB is detectable if it deposited the same amount of power in my instrument as dark matter did. So if you go through that exercise, you get the result I'm showing you here in terms of how much energy density in the CAB you would be sensitive to. There's 2 bits of bad news and 1 bit of good news. So let me tell you about the bad news first. We want to probe very small energy densities. And when we match this to dark matter has a very large energy density locally. I mean, it's not as large as, say, as on the Earth, but compared to the CMB, it's 9 orders of magnitude higher. So that's a factor of 1 billion that we lose at the outset. Additionally, although you can do some tricks to get over this, narrower signals are just easier to look for. And so you will lose from the fact that the CAB is less coherent than dark matter. So that's the bad news. But where the good news is that these relativistic axions could easily be very strongly coupled. We have no constraint on them being any more strongly coupled than from these star emission bounds. And as I showed you earlier on, these dark matter instruments are looking to get many, many, many orders of magnitude below the star emission bounds. So if you have a strongly coupled axion, which you might have expected in these scenarios anyway to produce an appreciable energy density in the early universe, then when we have a sensitivity well below that, you can win by an enormous factor squared to overcome the problems I told you about from the other 2 factors. So of course, this is a rough estimate. I can tell you I did the careful calculation in the paper, and I can tell you I'm only lying to you by an order 1 number here. It does get the parametrics correct. So what I can do with this is that I can go back to this plot I showed you earlier on, and now I can just take instruments and map them directly onto this plot using that estimate I just told you and being as optimistic as I can about how large the coupling is. And this is where you end up. You find that existing instruments aren't yet getting into the interesting parameter space, but future instruments like dark matter radio absolutely will. And I mean, there's a lot of takeaways you can have from this plot, but those are the two that come to me most immediately. So that's the main takeaway from this. As I go to future instruments like dark matter radio, I will easily be able to get into the parts of the parameter space where I could probe axions produced in the early universe. But as I move to higher frequencies, it's going to be more challenging. And this has also led to some of my thinking in lines of, as I told you, the candidate I really care about the most is this thermal axion background. But look, we are many orders of magnitude away from this. But having gone through this, maybe it's not so shocking that we're not able to probe this, because if you stare at this for a bit, the thermal CAB is in a parameter space where the axions aren't overlapping. They're really like a gas of axions flying around. It's not at all a coherent wave. Whereas the device of Mad Max is looking for some coherent wave of dark matter. An instrument built to look for a wave, it turns out, is not very sensitive of looking for a gas of particles. But that's okay, because there's various ways that we can look for gases of particles. Actually, one of them I told you about earlier on in the talk was the CAST experiment. That's effectively looking for individual axions coming out of the sun, moving down the dipole magnet and converting into X-ray photons. If instead I had a microwave version of CAST and I made it very large, like 10 meters cubed, there's some challenges associated with this, but I've been reassured by various experimentalists I've spoken to that this isn't totally nuts. I'm losing control here. What's happening? Oh, no, we're good. I've been told it's not totally nuts, and our hope is that building such an instrument, it might take a few decades, could actually get to where I think the thermal CAB would be, which would be incredibly exciting. So unfortunately, I've lost access to the... well, you go back one, please. Thank you. Awesome. So just to say, thanks for fixing that up. Yeah, just to say briefly, I think also I focused the entire talk today on the coupling to photons. And although that's where we have the most optimism in the search for axions, in principle, axions could couple to many other standard model states. In particular, earlier today, I was hearing about how super CDMS can very strongly probe the possibility that axions couple to electrons, and also they could couple to nucleons. There are many other couplings we could search for. And I've really gotten very interested in the nucleon coupling and the possibility not just of searching for dark matter, but also of searching for these relativistic signals. And you can see that NMR-based techniques, which are looking for these nucleon couplings, could also very strongly probe cosmic axions. But let me not get into this just now. Next slide, please. Again, the main takeaway I want you to have from this is that in the future, instruments, especially like dark matter, should be able to get to where we have these relativistic axions, and it could be another signal that they run into on the way to dark matter. So next slide, please. So with that said, what I want to turn to next is another possibility of a type of wave you could detect here that's different to these relativistic axions. It'll still be relativistic, but it will not be an axion. I want to tell you about the possibility that if a gravitational wave passed through these instruments, that you could actually see the signal. So this is going to be work that's, was done primarily with my collaborators Valerie Donkey and Camilo Garcia-Salí, and then this is really testing my memory here. But it was also done with some follow-up work that was done with amazing graduate student Sungmook Lee, and some recent work that I had with Dan Carney and Valerie Donkey as well. So next slide, please. So the main takeaway I want you to have from this part of the talk is just some intuition that you can even use these instruments to search for gravitational waves. Thank you. So in order to answer this on the next slide, I'll just quickly convince you how this is even possible. And the intuition is, let's just look at the action for electromagnetism in curved space. It has the form that I'm showing you up the top. Now, when I'm talking about a gravitational wave, I don't just mean an arbitrary curvature of space-time. I actually have something very specific in mind. In particular, what we usually think about is I have flat space that has been very, very slightly perturbed by the passing gravitational wave. And that's what's encompassed in h mu here. That is an extremely small size is what I'm showing you there. And now I really mean obscenely small. To give you some intuition, at the that experimentally this is going to be challenging, but from a theorist perspective, a great feature of this is that I can do all my calculations at linear order and I'm not worried about missing anything. So now doing the first calculation to that effect, what I can do is I can substitute this form of the curvature of space into the action for electromagnetism up the top, and I start expanding out. At leading order, I'll find Maxwell's equations in flat space. But at the first order where I have the gravitational wave, what I will find is I'll get terms of the parametric form hf squared. And again, not only will there be a g in the determinant here, also in the contractions of f it will appear. Now I'm being schematic. Of course, you're going to be really careful about the index contractions, but you will have something that is order h and something that is order f squared. And why that's interesting is on the next slide, you can see that there's actually quite a close analogy to everything we've been talking about in the talk today. There, I was looking at this coupling Ga gamma gamma A. Remember, A is a scalar field. It has mass dimension 1. Ga gamma gamma has inverse mass dimension. So I'm looking for some dimensionless quantity Ga gamma gamma times A. And ff tilde isn't that different to f squared. I mean, of course, in detail, there are critical differences. But in spirit, if I have an electromagnetic field and a gravitational wave passes through it, it will induce an electromagnetic response because of the presence of this term. So if we move to the next slide, what I want to show you is that in detail, this becomes quite hairy. I'll give you a flavor of some of the details in a bit, but I won't subject that to you today. I'd be very happy to talk about it offline. So what I want to give you some sense for is why should you even care about this? And to do that, I'll go through a 0th order estimate that I first did that got me very excited about this possibility. So in particular, let me take this overly serious, this analogy between these two, and say that f squared equals ff tilde. Then on the next slide, what I will see is that my sensitivity to the strain will be matched by whatever sensitivity I've had to Ga gamma gamma times A. So it helps on the next slide to write this out in slightly more detail. So on average, what is the value of the axion field? Well, it's 0 because it's just some oscillating field, but it does have an RMS value, and the RMS value is set by the square root of the dark matter density over its mass here. Now, it's also going to be helpful in a moment to do this. It turns out that Ga gamma gamma on average, as we expect to have a value of the electromagnetic fine structure constant, divided by 2 pi times the scale at which the symmetry the axion emerged from was broken. I know I haven't told you about a lot of this, but it's going to be useful for a reason I'll show you in a moment to rewrite it in this form. Another way of saying this is that if I want to determine the gravitational wave strain sensitivity, I can go and look at an instrument and see what mass did they probe. That gives me this parameter here. What value of Ga gamma gamma did they achieve? I can then determine an FA, and I can work out all of these factors here. But why this is interesting is on the next slide, I can tell you where all these instruments are heading. And if you recall, all of these instruments are moving toward this line that I call the QCD axion line. And there, what was the defining feature was that the stronger I was coupled, the higher the mass would be. And another way of saying this is because the coupling is inversely related to where the scale, the symmetry scale, the breaking of the symmetry scale at which this particle emerged, that scale has to be higher. So what ends up happening is for the QCD axion, the mass times this FA is exactly related to QCD quantities up to some order 1 number. In particular, it gets matched to m pi times f pi. So that tells me for an instrument that had sensitivity to the QCD axion, I know the strain sensitivity will be given by all these parameters. But I know all of these parameters. They're all known standard model quantities, except for rho dm, which I can measure. And so on the next slide, if I just put all of these together, I find a strain sensitivity of 10 to the minus 22 for these instruments, which of course is what LIGO achieved in their groundbreaking discovery. So I was incredibly excited when I first did this estimate, but then to tell you that 5 minutes later, there was a sobering realization on the next slide, and that is that the signals I really care about would even be further off than this. And the reason for that is the signals I care about most at high frequencies are these genuine signals of the early universe, where, for example, you have a high temperature phase transition. And what you can show is that that energy density also has to obey the same delta and effective bounds I told you earlier on. There can't be too much of it around, or we would have seen a modified expansion history of the universe. And to be consistent with those bounds, you find that you have to live below about 10 to the minus 27, so 5 orders of magnitude below this. Disappointing, but that is where we're at. And this means that if these instruments, although they could detect gravitational waves, they're only going to be some product of the late universe. They won't be able to see the genuine early universe relics just yet. So on to the next slide. So just a few words about, maybe 1 or 2 words about the real thing. Ultimately, the gravitational wave also modifies Maxwell's equations, in particular the inhomogeneous equations. It's somewhat involved. I had an experimental colleague tell me, I mean, you want me to be impressed by this, but I know at the end of the day, you're going to put it into Mathematica. So I don't know how much it matters, how long it is. But so there's some degree of truth of that. But another thing is you might actually stare at this for a while. And if you've worked with gravitational waves, you might say, hang on, I know a way of simplifying this. If I move to the transverse traceless gauge, I know that there'll be no temporal components to the gravitational field. And also all the trace terms will vanish. So I'll kill off all 3 of these final terms here, and life will be very simple. Unfortunately not. This is an error that a lot of people had made in the literature. And the reason for this is that in general relativity, a choice of gauge is also a choice of reference frame. And what my question then is, what do you mean by an electric and magnetic field in the transverse traceless frame? You might know what you mean in the lab frame. You've got a solenoidal or a toroidal magnetic field, but I can tell you in the transverse traceless frame, it will be some hideous oscillating mess that you'll first have to carefully understand if you want to then take advantage of the simplicity you have here. So if you go to the next slide, to give you a flavor of the subtleties that are involved, there's been a lot of work in this. We partly followed this very beautiful paper by Asher Berlin and his collaborators. It turns out that life is actually much simpler just working in the rest frame of the lab, where at least I know what I mean by the fields, and then I can just deal with the more complicated form of the gravitational wave. And for example, one of the surprises that emerges is that the leading gauge invariant contribution actually scales with frequency squared, when there'd been some claims in the literature due to confusions with which frame to work in that there was a linear contribution in frequency, but it's actually not a gauge invariant term. So if you go to the next slide, that's getting into the details. You have to keep account of all of this, but physically what happens is you have this magnet. Next slide, you'll see the gravitational wave passing through it. Next slide, and you will see a current being generated by the interaction with this. Now, unlike in the axion case, you'll generate a current in every possible direction, which in 3 dimensions is 3 directions. And then if you move on to the next slide, the currents have this slightly more complicated form, but yes, admittedly, I put it in Mathematica. And so if you go to the next slide, when the dust settles, you find that you do get a flux through this, through a pickup loop you put here due to the gravitational wave. Now you can see that I haven't put a loop. I put a figure 8 in here. Why did I do this? This confused me for about a year. It turns out that there are some selection rules associated with the symmetry of the problem that I'm studying here, that if I put a circular pickup loop in here, I'll get a very, very small signal because the symmetry forbids the leading order term appearing. Actually, we derived all of these selection rules in this follow-up paper we had with Sungmook Lee, showing that it turns out for this configuration, you can show that a figure 8 pickup loop is the optimal way you want to read the signal out. So on the next slide, what this means in practice is that we can get this sort of sensitivity to gravitational waves using an instrument like dark matter radio. It's comparable to a number of others that have been put forward. One of the nice features about this is we want to build dark matter radio anyway to look for dark matter, so you can sort of parasitically take advantage of this. But if I'm being honest, as exciting as that is, there's a challenge ahead. So on the next slide, let me zoom out and tell you about this parameter space more generally. So I was telling you about these enormous achievements we have here. But where we really want to get in this parameter space is down below this delta N effective bound that I'm telling you about, because this is where the really exciting signals are, like these hints of an early universe phase transition, or the signal that would just be amazing to see is that we actually know that the primordial plasma should have emitted gravitons. They can't have been in thermal equilibrium. The temperature didn't reach the Planck scale, but you can still athermally emit these particles. Essentially, you freeze them in. And that this spectrum holds a wealth of physics. It's sensitive to the reheat temperature. All the degrees of freedom that existed between reheat and today could be teased out if you could actually measure this. So that would be great, but you can see there's a few orders of magnitude between us and there. So I think really the question for the field on the next slide is, can we build instruments that are much more sensitive than anything we've put forward so far? I think the answer is yes. I'm very excited about this possibility that is highly preliminary, but just to say with Valerie Domke and Sebastian Ellis, we've realized that you can actually rethink of what a Weber bar should be. And thinking in that direction, we realized that we believe that the optimal Weber bar you could ever build is actually just a magnet. And if you use a magnet as a Weber bar, we can get significant improvements on what's shown here. Although, honestly, if you look at it in this broader parameter space, even though this is a few orders of magnitude improvement, it's still not getting to where we want to be. So we're going to need to get out a little bit more. So in the time I haven't left myself, but please excuse me to have 1 or 2 more minutes, what I want to tell you about here is just some other thinking that I was led to that actually led me, looking at this parameter space, led me to ask some question about the quantum nature of gravity that I never thought I'd get involved in. And the reason is that I've told you several times in the talk that a really useful way of understanding what types of experiments are going to be sensitive to these signals is to think about where are they behaving like waves and where are they behaving like particles. And there's nothing special about gravity. It's just some bosonic energy density. Why can't I ask the same question of it? Although I hadn't seen this done in detail in the literature, if you do ask that question and draw the line, you find it cuts right through the parameter space I'm showing you here, such that on the next slide, you find that to the left of this parameter space, you're looking for a wave, whereas to the right, what you're looking for is individual gravitons flying around. And so if you wanted to make a detection, you'd have to detect one of these gravitons. So on the next slide, some of you may be familiar, I was when I first drew this line, that there's a very famous paper suggesting that detecting a graviton is probably impossible. In fact, it was the last paper that Freeman Dyson ever wrote. It was technically a talk that he wrote up, but you know what his answer is going to be from the title, is the graviton detectable? The short of it is no. Of course, the reality is in the paper, there's some more nuanced arguments, but I think the takeaway that many people in the field had was that Dyson had proved it was impossible to detect a graviton. If so, that would be remarkable because it would show that that entire parameter space I'm showing you here is in principle unreachable if Dyson's claim was true. So once I drew this line, I got very interested in reading Dyson's paper and asking, what can be done here? In particular, CAST cuts through this line. So did Dyson make a mistake or did CAST make a mistake? I can tell you when I sat down, even though I know CAST are very careful people, I thought maybe Dyson was right, but let's dive into this. Just to say one word, what was Dyson's most famous argument on the next slide? He went through a thought experiment and he asked, let me take an interferometer like LIGO and think, can I make this instrument so sensitive that it can reach this line, which where LIGO operates at around 100 Hertz is obscenely sensitive. We're talking about strain sensitivities about 18 orders of magnitude better than what LIGO has achieved. And actually, through a beautiful thought experiment, what Dyson does by invoking the uncertainty principle is that he shows just by thinking about the size separation you need between the mirrors and the mass that these mirrors must have, the uncertainty principle forces you, on the next slide, for the whole thing to collapse into a black hole. The mass must be so great and they must be so close together that they exist within each other's Schwarzschild radii. So that would say that reaching this line with an interferometer would not only be challenging, it would be inconsistent with the laws of physics. And so because of this, I think many people had interpreted that you could never reach this sort of sensitivity. However, if you go on to the next slide, what that's the takeaway I had, and one slide further. If you look at higher masses, it's not at all obvious to me that something goes wrong. In particular, as it turns out, the energy density in gravitational waves scales as the strain squared times the frequency squared. So if I go to high frequencies, I'm looking at larger energy densities, and you can also see this line runs up. So I'm looking at larger strain. So actually my energy density will scale on this line with frequency to the 4th power. So I'm looking at a much, much, much more dense signal when I'm up here than I am down here. And so intuitively, it should be easier to see. And indeed, you can carefully check what CAST did. I did this, and you find that there's really nothing wrong with them. They absolutely can get into this regime and detect an individual graviton if you had a source there, which is somewhat speculative, but it's not inconsistent with the laws of physics. Indeed, I worked at CERN for several years, and at no point was I worried that CAST was about to collapse into a black hole. And furthermore, as impressive as CAST is, it's not the ultimate instrument we could imagine building within the laws of physics. So you could even hope to go much lower than this. So I don't think there's any reason that you couldn't detect a graviton. And then on the next slide, the last word I want to say about this, but this is a real can of worms that I'd love to chat about afterwards if people are interested in. Initially, the reason Dyson asked this question was because he thought if you detected an individual graviton, then by analogy with the photoelectric effect, you would prove that gravity was quantized, just as famously the photoelectric effect led to the line of thinking that light itself was quantized. However, and something I didn't realize, but I dug into, from a modern quantum optics perspective, it's just not true that you can determine from the photoelectric effect that the incident source must be made of quanta. In fact, we know you need to do much more complicated measurements like look for sub-Poissonian noise or entanglement in order to determine that the wave is made of quanta. And you would need to do the same thing for gravity in order to realize that gravity was quantized. So actually a measurement by CAST of a signal would be revolutionary. It would tell us that there's some amazing new signal up here that we hadn't anticipated, but it would not necessarily tell us that gravity was quantum mechanical, which turns out to be an even harder problem. So stepping back on the next slide, this is really getting into the weeds, but again, just to take you back, the one takeaway from this section hopefully you'll have is that you really can use these instruments as gravitational wave detectors. And then on the next slide, just to step back one step further, again, although it was my motivation, hopefully one of the main things you take away from today is that we're in an incredibly exciting time in the search for dark matter. I think axions are very, very well motivated particles, and we now understand how to build the instruments that can cover the parameter space. So either if you're not working in this field, it's just something you can wait for it to happen, or there's a lot of exciting work to be done in order to potentially discover dark matter with these devices in the coming decades. However, these are going to be some of the most sensitive instruments, or the most sensitive instruments we've ever built for these types of signals. And I think hopefully I've given you a flavor of today is not only could they search for dark matter, they could potentially run into all sorts of other signals as they do so. And hopefully I've shared some of this additional excitement I have for these searches with you here. Okay, with that, let me end it there. Sorry for going a bit over, but thanks for your attention.